Professor Suo is Alan E. and Marilyn Puckett Professor of Mechanics and Materials at Harvard University. He grew up in China. He received his degrees of kindergarten, elementary school, middle school, high school, and bachelor, all from the campus of Zhigang University. He did his undergrad research with Professor Xing Ji, and then he moved to Harvard and finished his PhD with Professor John Hutchinson. He was a faculty in University of California at Santa Barbara and Princeton University. He moved to Harvard in 2003. He's a member of National Academy of Engineering and the National Academy of Science. He's currently on an ongoing project of a long thread of Twitter titled 100 Years of Toughness to celebrate the landmark paper published by Griffiths in 1921. So today he has some plan to share with us on his plan to win the war on fatigue, particularly in the context of the COVID fatigue. So for audience, please, during the seminar, if you have any questions, please feel free to type your question in the chat box, or you can keep your question and you can speak up after the seminar. That'd be great too. So now it's on yours, Zhigang.
Thank you, Ke. Thank you everyone to come here. I will share the screen. Let's see. Share. Right. Okay. Does it work?
Yes, looks great.
Right. Okay. Oh. So let's see. Can I move something? Oh. Let's see. All right. So yeah, this is just a plan to win the war on fatigue. The kind of fatigue Ke explained to me today. He is worried about a COVID fatigue. I worry about that too. I have no plan for that. I'm thinking about a traditional fatigue in mechanical engineering. So I'll be more specific shortly. Oh. All right. So in mechanical engineering, we all know glass is brittle, it shatters, and metal is tough, it deforms plastically. So that's a common experience. Now for rubber, this rubber here seems to be different from glass and steel in some obvious ways, right? It's elastic. And it doesn't have much plasticity. So that's a three kind of thing. So in my field, I'm really particularly interested in something called a toughness. So if you have taken a course on fracture mechanics, or actually if you shatter anything, you know things will fracture. Now here's a little history about a fracture. We just heard 1921, Griffiths wrote a paper about a fracture of a glass. So he said the glass fractures because you have a crack. This crack break one layer of atomic bonds, all these other atoms remain intact. So the energy needed for breaking, to cause a fracture, this is what we call toughness, is about 1 joule per meter squared, amount of energy needed to create one area of a crack. So that was his theory. I have one more page about his theory from modern point of view, how this 1 joule per meter come about. Now, actually, let's jump to here. In 1948, Irwin and Orwan said, look, metal doesn't look like glass. It has a plastic deformation. I draw here, didn't even draw a metal. It's some kind of a gel. I'll show you specific chemistry as an example later. But the key point is for metal or a lot of tough materials, what you have, is an enormous amount of plasticity. Enormous in the sense much larger zone on the order of millimeter or centimeter scale, much larger than individual atom dissipate energy, plasticity dissipate energy. As a result, your toughness easily 1,000 to almost million joule per meter squared. Many orders magnitude higher than glass. That's our common experience. Steel is very different from glass in terms of fracture. Now, there is a model. Normally, we don't teach it in normal fraction mechanics course. It's called a Lake-Thomas model, created in 1967, specific for something like a rubber. So, and we all have a sense rubber is a lot tougher than glass. So these guys ask why that's the case, or what's going on from molecular picture. Here's the picture they have. Now, for a crack going through an elastomer, so first of all, elastomer, long polymer chains with covalent cross-link. It's in your mental picture should be a three-dimensional network of polymer chains. Now, it's true, when a crack moving along, you only need to break one layer of atomic bonds. That's true, same as glass. All the other atomic bonds, so even on the same chain, these other atomic bonds do not break. You only, for each chain, you just break one bond. That will cause crack. That's your experience, right? If you tear a piece of rubber, you don't have all the atoms flowing around. You just have two surfaces, right? Now, however, just let's take a look at this particular chain. Before it breaks, the entire chain is stretched to near breaking point. When it breaks like this, the energy of an entire chain is dissipated. So therefore, you need to snap a layer of chains, in the sense, dissipate energy in a layer of chains, even though you only break a layer of bond. As a result, toughness, of course, is higher because you have a more, typically hundreds and thousands or even more number of atoms along a chain. So that's why you have enormous number compared to glass. So that's in the nutshell 100 years of toughness, right? Okay, now let me show you some detail. So you probably all heard, look at this equation, Schrodinger. He created this equation a few years later than Griffiths. So Griffiths didn't know this equation. So Griffiths measured this experimental value, 1 joule per meter square. I'll show you roughly his experiment shortly. But he didn't know where this 1 joule per meter come from. But now we know where it come from Schrodinger equation. There's no engineering really needed. So you just look at it, this equation. This equation is interesting. So I write in this stationary form. This is energy. This is phi is a wave function. R is a distance. So I only write equation for this simplest model with 1 proton and 1 electron. So we're in a very lucky universe. All electrons are same. They have every electron has the same charge E and the same mass M, and this epsilon 0 is a permittivity in the in free space. It's essentially a universal constant. And this H bar is another universal constant. So you probably study this in high school, in college, whatever. And then you say this belongs to a certain kind of people do simulation, would do simulation using this kind of equation, but you don't need to solve anything because this equation, just by dimensional consideration, it has both a length scale and an energy scale. The length scale is just looking at this, because here is a length, and here del square has 2 lengths. So you just compare these 2 terms, you have a length scale. So this length scale is this. So I choose, put 4 pi here. So this is essentially the size of a hydrogen bond, this picture. Not hydrogen atom, proton and electron. And energy scale is, again, you have energy here. Just compare this energy and this term because they have to have same dimension. Now you already have this length scale. Just put it in, you have an energy scale. Again, I put these numbers in because these numbers are hydrogen bond, but I don't need to have numbers to know the order magnitude is on the order EV, right? So now, so we already know for Griffiths, all he needs to have is energy per unit area, meaning energy per A squared. So I use a more realistic number for atomic bond because hydrogen is such a small thing, even among atoms. So I do three times this 10 to minus angstrom. And EV, I just use EV hydrogen as also very tight bond, hydrogen bond. So if I do these 2 numbers, I just right away get 1 joule per meter squared. So 1 joule per meter squared has 0 mystery. And also you learned today, it is applicable, it's universal, almost universal for all materials, so steel, rubber, anything, you have this thing we call the surface energy, atomic energy divided by area. Okay, very good. So we understand Griffiths totally from first principles. Now, Lake Thomas model, this model we normally don't teach to students, not even graduate students. It's a very interesting picture, very simple too. So I already said the picture is when there's a crack coming along, the crack really needs to stretch the entire chain. And when I break a simple 1 atomic bond, the energy dissipated is energy, covalent energy of the entire chain, right? Even though I only break 1 bond, it's not a very intuitive idea, but these guys thought about it. So then the model is very simple. This is a scaling model, really just scaling. Should be energy is per bond. This is energy per monomer. So this is energy per volume. Then I need to times the thickness of this one molecular length thickness. I don't have time to go through this detail. This is called a random walk model because these chains, the end-to-end distance is measured by random walk, where B is the length per monomer, and N is how many monomers I have along the chain, has to be square root. So this is the thickness, a single chain layer. So that gives you a number. I'll show you numbers later. So that's in a nutshell what's a Lake Thomas model. It's a classical model. Right. Now, I also need to tell you just in 1 page how this idea of the plasticity work to give you toughness. Now, so we all know, oh, gee, this computer becomes super sensitive. We all know the stress strain curve, right? For metal, plasticity. So you, when you apply a load, this part is elastic, you can reverse, but starting at point B, you have yield, so you have a plasticity. When you, at any point you decide to unload, it doesn't go back. You have a hysteresis, you come back to D. So this area is energy dissipated as a heat. Some people call it plastic work. So doesn't have to be metal plasticity. Anytime you have a stress strain curve, have this kind of hysteresis, you dissipate this amount of energy. So that's a point. Now, suppose you have a crack going through something like a metal or plastic, anything has dissipation. So what will happen is you apply a load, want to push this crack ahead. So this crack not only need to break atomic bond, also cause a plasticity in a large scale, typically millimeter or 100 micron, very large scale compared to atom. So if you look at a material particle, way ahead material, the crack, so this part is still elastic. It's almost like here. And near as a boundary between plastic and elastic, so then you have yielding is here, right? And in the wake after the crack, because this stress is released, yeah, you maybe here you guys maybe still too close to the crack, you're still loading. But if you way in the crack behind the crack tip, you start to unload. So this process as the crack move forward, each material particle going through this ABCT, right? So each material particle going through this hysteresis dissipate energy. And now you dissipate energy over macroscopic scale, not atomic scale. That's why toughness is so high for metals. So that's a picture for metal. It was known in 1948. So, and this is a much later picture of what happened to something like rubber. In my group, we work with a soft material. For rubber, we all know it doesn't really undergoing plasticity because you stretch a rubber, when you release hand, rubber comes back, right? So, yeah, let's see. Yeah, so as a result, so most people say, oh, if I measure stress strain curve, this curve look like elastic going up and then elastic going down. There's no hysteresis. That's not true. It was discovered also about 100 years ago that natural rubber has this ability to crystallize under stress. So when you stretch rubber, this rubber chains become straight and they crystallize. When you unstretch, release, and this crystal melt. So you have stress, you form crystal, and then you release the stretch, it actually melt. It actually has a hysteresis. So it was known for nearly 100 years. So these people even measured, the same group of people, even relate this hysteresis energy. So there's a hysteresis, this hysteresis, a blue shaded area, correlate with the total work you put in. That is a load, unload, and when you fracture, you release the entire energy under the load curve. So these people actually tested many materials. They published paper a long time ago in Nature. They said these two quantities, the work of fracture, is correlated to dissipation, hysteresis, energy. So when your hysteresis is big, you have a very big work of fracture. If your hysteresis is low, like going up and going down along the same path, you have very little toughness. So this view was unchallenged for many decades. I'm sure, I don't know, Thomas, if you teach fraction mechanics, you probably keep telling students, I tell students too, if you have on a high tough material, you want to have high dissipation material. We keep perpetuate this view published in Nature and held strongly by most engineers and people in street. That view turns out to be wrong. This is what I'm going to tell you. So I keep talking to you about this quantity, joule per meter squared. I want to give you some physical idea, but most people don't work with this quantity. So joule per meter squared is the same as Newton per meter. So the way we measure it, or a way to measure, many ways to measure it, is if we have a soft material, I'll work mostly with hydrogel. a soft material. What we do is I have this soft material. I want to tear this apart. I use two stiff material like a plastic, a backing layer. So one backing layer on top, another backing layer on the bottom, and I peel it apart. This is called a peel. So, and I measure force as a function of time. So initially, when force is really small, the front doesn't move forward. You just cause more blunting. So at some point, the cracks start to move steadily forward. So this is steady state force divided by width of the sample is force per length. So that's the quantity I'm talking about. So I also mentioned to you 1 joule per meter squared, this atomic number. That force actually is very small. This is the toughness of glass. We all know 1 Newton is about 1 apple. You need to distribute 1 apple's weight over 1 meter. That's a tiny force, right? We all know that. So that's a sense of 1 joule per meter squared. That's for glass. Now you have a sense of a connection between glass and apple and a meter. Now, here's another way to measure it. I won't go to detail. The only thing I need to tell you is if I have some rubber-like material, all I need to do is grip this material and make an initial cut and pull this. When I pull this, this crack opens up and blunt it, and at some critical amount of pulling, this crack starts to move forward. And that's the point we measure toughness. Many toughness is measured this way. This has a long history created by, another name, Thomas Rivlin, a giant in the field. Both people are giant in the field of rubber science, long time ago. So these are basic tools, how we get this quantity, we call energy release rate, joule per meter squared, how we get this quantity experimentally. All right, so now I'm ready to tell you about fatigue. Fatigue, it's not a COVID fatigue, it's a mechanical fatigue. So the observation was first systematically reported by Thomas, this guy in 1958. So he was testing rubber. Now this phenomena looks like this. If I make a little cut here, and so we already know if I need to cut this, need to tear this apart by just a monotonic loading, just keep going up until the crack just jump ahead. That is a toughness. For natural rubber, this number is easily 10,000 joule per meter squared. Very tough material. You can try it yourself. Rubber, very tough material, much tougher than steel, than glass. This is called toughness. Then he made a discovery. He said, if I do cyclic loading, going up and down, then watching this crack, so the stretch as a function of time, going up and down, and then this crack will go a little bit ahead each cycle. This is called a fatigue crack growth. This is what mechanical engineers talk about fatigue. That is a measurement. So then he measures this crack extension per cycle, DCDN, as a function of G. G is how much load I apply in the unit of a joule per meter squared. He said, if I apply smaller load, smaller than toughness, then I will have, smaller growth per cycle. So if I make load even smaller, then growth per cycle would be even smaller, maybe 1 micron per cycle, maybe 1 nanometer per cycle, maybe 1 angstrom per cycle. But when load is really small enough, the crack will not grow anymore. That's safety. This quantity called a threshold for natural rubber is 50 joule per meter squared. The discovery was made in 1965 by Lake and Lindley. This discovery has been standing there for all these decades until very recently. So natural rubber is fantastic, but if you make a cut, you can do this experiment yourself at home in kitchen. Just do cyclic loading, the crack will grow. And the threshold is many orders magnitude lower than toughness, monotonic loading. This is also common experience for steel. You also know that, right? If you have a bookbinder or pin, you just go back and forward several times, the steel will break, right? So that's fatigue, crack growth. So that was a discovery. So as I told you, discovery was made almost as old as me. So same age, right? So it's a young discovery, put it that way. Has been there for all these decades and waiting for us to break this record. So I think I'm very excited about breaking this record. Not only for rubber, eventually I'll tell you about other things as well. I think it's a generic. All right, so now this is a picture from this famous Lake Thomas paper, 1967. The point they were making is, yeah, your toughness is way higher here, right? But your threshold is here, 50 joule per meter squared is the old unit. This number is 50 here. So remember, for natural rubber, you have a potent hysteresis mechanism by crystallization, strain-induced crystallization, and when you reduce the strain, you melt. There's a crystallization, melting. It is a wonderful material, right? Wonderful material. This hysteresis gives you this enormous toughness, 10,000 joule per meter squared. Now, if you shut off all this, melting and so people do experiment. What if you do experiment at a slightly higher temperature, so you cannot crystallize? Then you only have a threshold. This is a Lake Thomas picture. This is a chain is being stretched all the way to covalent bond, and it's elastic unless you zip it. And this is a threshold. So their paper say, you always have this threshold for you. It's a small, it's always there, 50. So our game is first give the name to this mechanism now. It's a more generic name. We call it elastic dissipator. It's elastic until it breaks. But when it breaks, it just dump all the energy along the chain. So our task is to amplify this elastic dissipator always all the way to 1,000. Then we will have a really, really fatigue resistant rubber. Right, that's a game. That's good. This part is not even planned. I want to show you our result. The plan is for the rest material. How about a steel? How about a ceramics? All these composites. Purdue is very big on composite. So that's a planning part. Okay, now so let's first tell you what we have already done, the basis for the plan. So the material, I need to tell you a little history of a material I've been working on for last a decade or so, more than a decade now. It's called hydrogel. So hydrogel has this molecular picture. You have a polymer network, almost like a rubber, but it also has a lot of water in it. 90% water typically. But people are familiar with the hydrogel. So your food, lots of your food, tofu is a hydrogel, and jello is a hydrogel. People are hydrogel because your body has a 70% 70% water in it. So your brain is hydrogel, for example. Now your liver is hydrogel. Anything, your bone is hydrogel. Everything is hydrogel, right? The only thing non-hydrogel is blood. Blood is not hydrogel, but blood flows. All right, good. But of course, in terms of synthetic hydrogel, it has a relatively short history, starting in 1960. The first application is a contact lens. We all know contact lens, right? It's hydrogel. And in 1980s, people develop a super absorbent diaper. These are massively produced application for hydrogels. They only follow food. Food, I guess, is the biggest market of hydrogel, right? Okay. Now, in more recent time, we, of course, have artificial tissues. I should give you some examples, the kind of thing we do. A lot of people do this kind of thing, ongoing research. Because a hydrogel is very close to food. And where do you get food? You get food either from plants or from animal. You get food from life form. So hydrogel is a very close relative to life. So it's not a small wonder that hydrogel is such a hot topic in recent decades because people worry about health. Right? Okay. Now, so this is one landmark work, 2003 by Jianping Gong. She was a Chinese, but by now she's a Japanese. She works in Japan, professor in Japan. She published a paper almost 20 years ago. So most hydrogels look like this. Here you have a hydrogel like tofu. And you have a hydrogel, you have a metal piece, it's an instrument machine, you compress it, it breaks like tofu, right? And she created hydrogel. So you compress it and it become pancake. When you remove the load, it stand up. It's like a rubber, right? It doesn't shatter. Wonder material. So it was a sensation immediately after her publication. So the way she did it was she used, it's called a double net hydrogel. She has two networks. One is this blue network, very tight network, short chain network, and this red network with a long chains, very tough chains. And this is a blue network, very brittle, blue and brittle, yeah. So these two colors are colored a long time ago, has nothing to do with this election, just occurred to me. It's a mistake. Next time I'll change this. But in this case, blue network and red network all contributed to the toughness. How's that? So that's good. So what happens is the following. When you do fracture, this blue network is so short chain, it's very brittle. It breaks, but red network doesn't break. However, when blue network break, it break over large room, large space, on the order of 100 micron or so. That dissipate a lot of energy. So it's a mechanism, new mechanism of plasticity using two networks. That's her work. So so we were the follower of this work. It took us a long time to publish this paper, but we eventually published it in 2012. So here's our gel. It's a highly stretchable, and at that point, break some record. So, this is our hydrogel. It's a hydrogel is transparent. You see a black background. So hydrogel is this big, and we grip it with the two plastics, and then we pull this 21 times, doesn't fracture, has a rubber-like feeling, right? And remember how we measure toughness. We need to make a cut and pull this again, and until the crack pop ahead. So when we do this material, we pull this 17 times, the crack doesn't pop, doesn't move forward. So that translates to toughness, almost 10,000 joule per meter squared. I was very disappointed the student couldn't make it 10,000. The 10,000 is a landmark, it's natural rubber. So by now we and other already break this record. This is a 2012 record. Remember, this material can have about 90% water and almost as tough as natural rubber. In comparison, tofu, jello, people have a sense of this number, 10 joule per meter squared. And most gels, 10 joule per meter squared. Contact lens, we just showed 100. Cartilage on human toughest material inside body is 1,000. natural rubber 10,000. So this was a sensation. And also this paper got a lot of citation by now, also because it shows a simple principle. You can do something like this. It's called a weird algebra. You have a brittle plus brittle equal to tough. So this is how you do it. I already told you about this one network. If you have a very stretchable network, look like a spring, and you have a energy, we measure it as a typical hydrogel polyacrylamide, 100 joule per meter squared. So that's what you have. And we have another hydrogel. It's coming from seaweed, biopolymer. And you have one chain here, another chain here. In the natural state, it's cross-linked by ion, calcium, because on the chain you have some negative charge. Calcium ions have positive charge, they zip up. So, but this alginate, it's called alginate, come from algae, kind of algae. Has kind of like tofu. So when crack coming along, you need to unzip here, but you do not need to unzip off crack plane. As a result, you only unzip one plane of calcium cross links. That gives you 10 joule per meter square. Again, this is a measured number. We don't compute this, so we just measure it. Okay. Now, our material is a wonder material. What's going on? Oh, yeah, today the computer is acting up. So our material, we just mix these two materials together. Both are very traditional material. If you're in the hydrogel business, you would know these two materials. But we were the first people actually mix them and measure its toughness. So now this material is very tough. See, the two very brittle material get very tough material. So this is brittle to plus brittle was equal to tough. Now, if you teach fracture mechanics, this will not surprise you. But a surprise almost all chemical engineers, chemists and biologists, they saw this as a black algebra. So this black algebra has very simple physical reason. So what you do is, so here's a crack. Now, before you break this polyacrylamide chain, long chain, you unzip many of these calcium bridge over very large volume. In our case, in over the centimeter scale. That's why you dissipate so much energy. It's not a small wonder. Since this paper has published, just the world just set this on fire. There's so many recipes making tough gels, different chemistry, different numbers. This record has been long broken. People don't compare this number anymore. There's no meaning. You can have an infinite toughness now. All right, so that was very good. So very good. So then people keep asking us, ever since this paper was published, they ask, Zhigang, you teach fracture mechanics, right? So we all know the problem with all tough material is a fatigue. How is the fatigue property of your material? We keep mumbling. I actually, back in my mind, I know fatigue cannot be very good because it has such a huge hysteresis, almost like metal. If metal is bad for fatigue, this gel must be bad too. So I have been avoiding this problem until we exhausted all the low-hanging fruit. So I have one student in the group who did something. So let's say we start with something simple. Let's just do this polyacrylamide. Polyacrylamide, we said it's nearly elastic, like a spring, right? Spring is not supposed to be fatigue, it's an elastic system. So here was my hypothesis. An elastic network will not suffer fatigue, right? So Thomas, you're there, right? You must agree with me. It's a reasonable hypothesis. So the poor student tested for nearly 2 years. He has fatigue. So I refuse to publish until he has no fatigue. But then at the end, I'm a reasonable scientist. I admit defeat. I sent concession to him by publishing this paper. So the paper finally was published in 2017. My hypothesis was wrong, and this material suffer fatigue. Let me show you the experimental picture. Before I show picture, I first show you this material is nearly elastic. So we stretch double the length, or even 9 times the line length. It's a huge stretch. You can see the hysteresis loop, especially after 1 or 2 loop, the hysteresis is just negligible, So this is a nearly elastic material. Polychloride has a near perfect elasticity. So I have some ground to believe this material is fatigue free, but I have to accept the defeat, right? So people have to accept defeat. Doesn't matter who you are, right? So here is a gel in front of a reality. So fatigue of a hydrogel. So here is an experiment. This material is transparent. Again, this is a black background and a beautiful piece of material. And we stretch up and down cyclic loading. And before we do experiment, we already put red marks here so we can watch whether crack move ahead or not. So far, the crack doesn't move ahead, but that's only a few cycles. For fatigue people, serious professional fatigue people, they need to test this a million, billion cycles. So, right now the crack is still at the first mark. Let me accelerate this thing. So, so just move forward. So this already approach second mark, right? So under cyclic loading, even in this very elastic material, nearly perfect elastic material, still suffer fatigue. Yeah. So yeah, my hypothesis was wrong. This poor student finally published his paper. He by the way, both students now are professors. Yeah, this is my colleague, next door colleague, Yusuf Velasek. So we published this paper. In that paper, we couldn't even propose a mechanism. We speculated things, why we failed. Yeah, at the end, we just mumble. Even to this day, this is a new form mumble. After 2 years, we still mumble. Here's the mumble. A new hypothesis, why nearly perfect elastic materials still can suffer fatigue. So if you have a crack in really perfect network means each chain is identical. So then you have a strain concentration, right? When crack coming along, you break this, break this, break this. All these other things will not break. So you should not have fatigue. Either the chain break or you don't break. There's no fatigue. Cycle make no difference. However, if you have a realistic network, realistic network is not perfect. It's not perfect. So some chains are shorter than other chains. So this black chain may be longer. This chain may be shorter. So when this crack is coming here, maybe this chain doesn't break. You already break this chain because this chain is too short. So all these short chains, when you do monotonic loading, all these short chains really contribute to toughness. That's why you have toughness, height in this case, 100 joule per meter squared. Now, however, if you do cyclic loading, maybe you already break this chain in the previous cycle. Then of course, your next cycle, you will not benefit from this anymore. So cyclic can grow, right? So that's our hypothesis. We don't know how to really definitively prove this. We are engineers, so we move on. We have some understanding of what's going on here. So finally, we have this courage to test this tough hydrogel with a tremendous hysteresis, right? With this unzipping. First of all, this material, this we knew for a long time, has enormous hysteresis if you just test it without crack. Enormous hysteresis in the first cycle. After first cycle, you unzip a lot of ionic bonds. The second cycle, later cycle has a tiny hysteresis, but it still keep damaging, even after this is how many cycles, 10,000 cycles, something like that. Yeah, you keep damaging. It's not a great material if you're an engineer, right? Okay. So if we test the fatigue, cyclic fatigue, DCDN, growth per cycle as a function of energy release rate, indeed, threshold is 50. As bad as natural rubber. Remember, this material is as good as natural rubber in monatomic loading. So 2017, after 5 years of our Nature paper, we were not too embarrassed to tell the world our material was not very good, but as good as natural rubber. So it's not terrible. Natural rubber is a gold standard for a while, right? Yeah. So that was the status. So we need a new idea. So this hysteresis giving you a lot of toughness. This old story, you make new material, but it suffers old fatigue. So we need a new idea. Here is one new idea. It's what we now call elastic dissipator. We published very recently now, last year. Now, the idea is actually very simple. It's an idea people in fiber reinforced material would know. So here we have a fiber. Our fiber is an elastomer, stretchable material. And the matrix is also stretchable material. But a matrix is more compliant than fiber. Fiber is maybe 10 times Young's modulus than this matrix, right? Soft matrix, stiff fiber, but the fiber is still stretchable. Both are elastomer because we're interested in making soft materials. Now look at what happens. So mark one material particle by a square. I'm gonna put a square marker here. So we know because this material is so soft, this matrix so soft, and when I load this material, I will have an enormous blunting because matrix can shear. So I represent shear by a parallelogram here, the material sheared this way. And look at the next fiber. So because there's an enormous blunting, I deconcentrate stress. The stress is nearly not concentrated at molecular level anymore. I deconcentrate all the way to macroscopic distance. This distance is governed by how large the fiber is, right? So in our case, this distance is easily millimeter or centimeter. Now, this is an elastic dissipator because both matrix and the fiber are elastic. There's no other dissipation mechanism. Before this fiber break, everything is elastic, it doesn't suffer fatigue. So, and when it break, it dissipates energy over the entire length of the fiber. So if this is your stress strain curve, your the work of a fracture underneath the curve is WF, but your toughness is the length, H, macroscopic length times this WF. This is an enormous number. So how enormous? So we did a measurement. So I already told you how we measure toughness, how we measure hysteresis. In particular, we're going to report hysteresis as a ratio. This hysteresis loop, this area WD, divided by the entire area under this loading curve, WD over W. So when this number is 0, you have no hysteresis. So these two curve, loading, unloading curve, match. This is elastic, purely elastic. If this number is 1, it means just a total, metal is almost like 1, right? Natural rubber is somewhere in between. Okay, now for polyacrylamide, it's less than 10%. All right, now here is our result now. Toughness and hysteresis. Remember this old 1966 Nature paper correlation between hysteresis and worker fracture and also toughness is in order to have a tough material, you really need to have highly hysteresis material. So metal also belong here. All the rubber you use, synthetic and natural rubber, it's here. Including our polyacrylamide alginate hydrogel and the Jamping-Gong's double network hydrogel. Their hysteresis, double network elastomer, and also elastomer, all these materials. Now, if you think about application of metal, we seldom use hysteresis of a metal in application. First of all, it's suffer fatigue. Second, you dump so much energy into as a heat, and you can only use it once. It's not very good material. So all these materials are troublesome, except for natural rubber. Of course, natural rubber is interesting because the metal crystal is forming and melting, forming and melting. So give you a feel you're coming back to the origin. However, it dissipates. Now, if you do unfilled without carbon, also test at a relatively small strain, then natural rubber actually have a very small hysteresis. Hysteresis is less than 10%, less than 10%. So for many years, people know only very few materials, such as natural rubber, can give you natural small hysteresis and high toughness. Natural rubber does this. Now, with our design principle, we just make a PDMS, enormous toughness and very low hysteresis. People play with PDMS. No, PDMS has a very low hysteresis, about less than 10%, few percent. But PDMS of pure PDMS has very low toughness, about 100. By making stiff and soft PDMS, making it a composite, stiff PDMS and soft PDMS, you easily lift up the toughness to, as high as natural rubber, once again. And this material is fatigue resistant because it's an elastic dissipator. So, and we demonstrate, this is another material, similar principle, we matrix use a hydrogel, and the fiber we use PDMS, and we measure the cyclic loading, and this is a kilojoule per meter squared. So if we do monotonic loading, the toughness, so this is the number of cycle. In the first cycle you break, this material has a 4 kilojoule per meter squared. Very tough material, like natural rubber, right? However, when we do cyclic loading, the student only willing to do 10,000, more than 10,000. So we say this is a threshold. It's more than 1,000 joule per meter squared, just by this mechanism. So, so here is a photo. If you have a higher load and you have damage here. If you have a slightly lower load, you have some other form of damage, But if you are at this load, 1,000 some joule per meter squared, and after so many cycles, this is you're going to cycle down, and you don't see any growth, no growth. It's a threshold. So that's a very simple mechanism. All you need to do is a tough, hard and a soft composite, and you have a high threshold. So I need to wrap up a song. So let me tell you the result. I will put these slides online after the talk because I have to jump over a lot of subsequent work. I want to reach punchline. I'll put slides online. Now, so this is the threshold as a vertical axis as a function, and compare with the toughness. We already know for something like a natural rubber elastomer, right? The toughness itself can be enormous, 1,000 to 100,000 joule per meter squared. This is the elastomer, but the threshold is less than 100. That's the elastomer. But our material can reach a threshold about 1,000, and a very simple principle. Very simple principle. So again, it's a principle is mechanical, has nothing to do with chemistry. You can make zillions of materials, depend on your chemistry. So here is a different chemistry. We start to learn something about 3D printing. We print. It doesn't have to be fiber anymore. Any structure will be good. So we print one network, a frame. So this is schematic. This is actually printed structure, red, and we fill the between with another soft matrix. So once we do this way, have a honeycomb, square, and a fiber, and these material, we test them. And this material, this work, it just has an enormous threshold. This guy is 700 or so threshold unheard of before for any rubber. So this is all existing rubber, commercial rubber, including field or whatever you do, it's just no good in terms of threshold. Natural rubber, a gold standard, not very good in terms of threshold. All right, so so I have several other examples. Let me just jump to one application example. Again, I apologize. So let me give you one application. So this is one application we made with a bioengineering group, David Mooney, my same floor neighbor at university, used Velocic again. And all these students, these two students are professors now. So, so here is we make a adhesive, tissue adhesive, hard from pig. So we first do a peel test. So this is our tough gel. You can see very tough. I cannot tell you how high the force is, right? You cannot sense it, but you can see the stretch. Meanwhile, while you stretch, you have a very strong adhesion. We develop a method to have a very strong adhesion. The adhesion by this peel test we tested is on the order of 1,000 joules per meter squared. Several hundred to 1,000 joules per meter squared. Very tough adhesion. For these things, people know for decades what they know they need. A need created for decades, wound closure and drug delivery. So this video was a world first video that shows tissue adhesive can be this tough. It's a world record. By now, there are many demonstrations now, different chemistry. Again, we illustrate. I didn't have time to illustrate the chemistry. Yeah, I'll skip this. The chemistry is really very mechanical kind. Many chemistry fulfill this principle. Anyway, then this Lee became professor. He was a student in my group and youth group, shared student and became postdoc at Mooney's lab. When he's at Mooney's lab, he created this work, tough adhesion. And then he became professor. He published a paper. He showed this fatigue threshold is about 10 per meter squared. Again, threshold adhesion is very low, very low. So then here is our paper. Now we find a mechanism just by elastic dissipator. We can have adhesion energy all the way, fatigue threshold, multiple hundred joules per meter squared. Again, this principle, all we need to do is have a very long chains as an adhesive. Your adherent could be anything, could be even hard material, could be steel, doesn't matter. All you need to do is have a very long chains, and you have enormous fatigue threshold. So the general proposal is to take this as a lesson. I didn't have time to talk about these other papers. So let me go to the summary. The summary is important. So I rushed through this. I believe this is a genuine breakthrough in the entire mechanical engineering. It doesn't matter what you do. As long as you deal with the materials, hardware, and want to fulfill some functions repeatedly, fatigue is an issue. And fatigue has been known engineering problem for more than a century. With a record, written record, people do experiments more than a century, was an unsolved problem. I think in recent years, we cracked this thing open by this simple idea, elastic dissipator. So elastic dissipator, we already demonstrated with a few materials. I showed you one with a detail, but even we demonstrated several materials. It shows high toughness, very low hysteresis, and extraordinary, unheard of high fatigue threshold for any materials. So I think we should go making a plan. Not many people worry about a hydrogel or even elastomer. People want to worry about the plastics, want to worry about the composites, want to worry about metals. How can we develop this idea, elastic dissipator, for metals, for example? So let's plan. Let's plan. So I have a long thread of tweets on the celebration Ke mentioned to you. So this story keeps going on. The publication is too slow. Tweet, you can tweet, right? Tweet. So our president tweets a lot of tweets every day, very influential. I try to influence people as well. Maybe one tweet a day. 100 years of toughness. Thank you very much.
Thank you so much, Zhigang. This is excellent. It's always educational to me, to myself. There's a few questions lined up in the chat box. And also, if you have other questions which you didn't type, please feel free to unmute yourself and you can speak up. Since it's a virtual, I don't think we have to say when we have to finish this. So I need to go in about 10 minutes for my class. So let me just ask you some simple questions. So since Zhigang was my teacher of fraction mechanics, so I'm not afraid to ask some simple or even naive questions. So Zhigang, I think for your elastic dissipator mechanism, it involves length scale, and it needs to dissipate the energy over some length scale. Where that length scale come from?
Oh, in our case, it's a very good question. It's similar to fiber composite. Ultimately, it's limited by so in our fiber case, right? It's scaled by fiber diameter. It's just like a toughness of ceramic matrix composite. It also has a length scale. That length scale is a ceramic matrix fiber diameter. Okay. But the stress deconcentration length is much higher than fiber diameter. Scale with fiber, because if you think about, if your fiber has very little friction against matrix, you can deconcentrate stress over the entire length of the fiber. But if you have little friction, this deconcentration becomes smaller. Okay.
Yeah, I think that's what I thought initially. Then this reminded me another question. So you showed this Lake Thomas figure that crack length per cycle versus the hysteresis. And when it has a higher hysteresis, then this fatigue threshold is higher. Is that correct? Then where is there also, I think essentially the question is why. So why is there any length scale also involved in that relationship, that a higher hysteresis versus a high threshold of fatigue?
No, you remember, no, maybe I wasn't clear. This is an old Nature paper, 1966. The plot was a horizontal axis is hysteresis. It's this energy in the loop, hysteresis. So it's energy. It's energy per unit volume, right? The vertical axis is work of fracture. It's you load it up and you fracture the entire work of fracture. It's also joule per meter cube. the correlation between these two quantities. That's a discovery. It's not about a fatigue. There's no fatigue. It's not a cyclic loading.
Okay.
So Lake Thomas' conclusion, and it's verified by many experiments. For example, natural rubber, you can, for example, if you have a synthetic rubber, it doesn't do this crystal melting hysteresis, right? You have the same hysteresis. Oh, no, same threshold as natural rubber, about 50 joules per meter squared. So for all rubber.
Okay.
So even natural rubber has this hysteresis, does not enhance threshold. Then people later on throw carbon black into natural rubber. Carbon black enhance toughness and hysteresis dramatically by order of magnitude, does not change threshold. So there's a threshold for natural rubber. It was a fixed number, fixed for many, many half century.
Okay, all right. Yeah, another quick question. That so you show a lot of molecular level picture, which is very intuitive and easy understanding. And for a mature chemist, how to validate those atomic or molecular pictures? Those mechanisms pictures seems very reasonable, but how we can, for example, can we check up on the chemistry on the frac tip or to validate those molecular pictures?
That's a very, very good question. You should read 100 years of toughness more diligently. That took enormous patience. For example, natural rubber has a clearest history. Published paper, because natural rubber, this cross-link was discovered by American, right? Goodyear, by trial and error for many decades, for half century. People didn't know what was happening to natural rubber, didn't even know natural rubber has long chains. You know, he discovered this thing, because natural rubber, of course, was known to Native Americans for 1,000 years. I guess at least we didn't have any written record. Native Americans know this molecular picture. Even Goodyear in 1850 or something, did not know natural rubber has a long chain molecules, and did not know what he did is making sulfur crosslink. Did not know. Took many, many decades later. So the guy actually proposed all these polymer long chain material, actually won Nobel Prize, right? So Goodyear actually died very poor. He did not win Nobel Prize, but he should. He invented these crosslinks. Yeah, it took many, Also, the natural rubber form of crystal, that can, you just, all you need to do is shine X-ray to, while stretch it, you'll form patterns. That discovery was made 1925, many years later. And the connection between this thing melting and crystallizing with a toughness is many years afterwards. Patience. But once you know these stories, of course, we have many tools to know things. If this is a crystal or not, shine X-ray, right? If calcium chain is calcium bond is do anything, I remove calcium by doing ion exchange, put sodium in. Let's have a lot of sodium, flood all the calcium out. And we do that experiment to show you don't have toughness once you get rid of calcium. Many experiments can be done. So that's why all these historical records are very important, how people learn about things. What's wrong with a lot of textbook today, especially fraction mechanics textbook, didn't tell you how discoveries were made. Then you can only be engineer. You cannot make discoveries.
Thank you very much.
Thank you.
Thank you very much for enlightening me about that. I'm a modeler, so it's a very interesting history and great story. So before I leave, there's still a bunch of questions there. Before I leave, I want to quickly announce that there is a social hour after The seminar, I already sent the link to everyone, every participants here. This is open to public. If you're a non-Purdue, feel free to participate. If you have used the Gathertown, this is very much like a game, and people just enter the same room, and then once you see someone within your distance, then you see their face and chat, pretty much like a conference room. So I enjoyed it. I encourage everyone to use it after this seminar. So I need to leave you a couple of minutes. So Thomas, are you still there? Can you help to other questions?
Yes, I'm here.
Okay, thank you so much.
Hey,
So
Thomas.
there are a few questions there. If you could, I don't see why we need to rush to finish this. I 100% enjoy this conversation and insights from Professor Suo. So there are a few questions there, but I have to go, and I will let Thomas take over.
Okay, very well. Well, again, thanks for the seminar. Very interesting idea. So I really appreciated the idea going from the molecular scale to the micro or macro scale in some ways, and translating that. So that was very interesting. And yeah, winning the war on fatigue, that's certainly dear on to my heart and my research group as well. So there, I will send you something offline here. What we have been doing, not experimentally, but with one of the graduate students, we have some things that I'll share with you.
Thank you.
Metals. But I'd like to maybe give students a chance maybe here and get to their questions as well. So one question was, do you have any idea on fatigue in non-correct or non-pre-correct samples? Are there any? Do you have any insights on that?
Yeah. Well, so I guess the most straightforward thing to say is if you don't introduce natural crack, right? It's a known, for example, for glass, we already know there's always a natural crack inside glass because any floor beyond 1 nanometer is a crack-like floor. So in that case, if you don't introduce crack, you just deceive yourself because there's a crack in the material.
Yeah.
For rubber, that length scale, natural rubber, it's known that length scale become 50 micron, 50 micrometers. So for many years, it's assumed as an engineer, you almost have to assume such crack exists in your natural rubber goods. So the game really is designed to lower your load so that you do not exceed, your threshold do not exceed this level. Then you have immortal structure. Or, Thomas, you know this, you teach this, you say, okay, I can let crack grow as long as I know I finish my service. I only need to have 100 cycles. For most applications, that's probably good enough. You let crack grows, design according growth. So in both cases, what you need to do is have a good enough material so your threshold is very high, and the growth per cycle is low enough. So the design principle is actually focused on threshold. Yeah. You do not ask questions you don't know about. Do I have a crack here? You assume you.
In that sense,
yeah.
How does this translate to the elastic dissipators? Do the elastic dissipator length scale then start to override that natural length scale somewhat? Yeah,
that's a very interesting question. So we should keep going this length scale. So we know, glass is about 1, and natural rubber is about 50 micron, and our polyacrylamide hydrogel is about 1 millimeter. So it's possible to design material, tough material, to have a larger and larger length scale. Now, steel is one very good example because people know a lot of things about steel, right? Steel, first of all, different steel, different heat treatment, different composition, they have different length scale, right? So the length scale typically go from 100 micron to even centimeters. Very tough steel, centimeter. It means if you cut the steel with 1 millimeter, you have this experience, right? If you stretch it, the crack does not really grow from this crack just plant. They ignore your cut. But if you cut, even for very tough steel, if you cut 1 centimeter, it will grow from there. So 1 cent. However, under fatigue loading, these lengths will become dramatically smaller.
Yeah, yeah.
For steel, the typical length, I would say, maybe all the way to, a micron, 20 micron. That's why all metallic structure suffer fatigue crack growth. There's no exception. You have to design below threshold level.
Yeah. So there was another group of question that was posted on the chat was related to rate dependency in these in the material systems that you're looking at. So what's the specific reason for the 0.25 hertz beyond the time that somebody can spend in the lab? Is there temperature sensitivity, and that's probably similar to time temperature superposition in some ways on that. Yeah. So I don't know if you have any comments related to these sort of questions that the students posted that were posted in the chat.
So some materials are rate sensitive, but the basic idea is not rate sensitive. For example, the material we demonstrate using the reason we choose this PDMS. PDMS is not very rate sensitive. So for example, you test the stress strain curve at different. First of all, if you test PDMS under cyclic loading, the hysteresis is very narrow. I already showed you the data. It's less than a few percent, very low hysteresis. And if you test at different rate within reasonable range, it hardly see any sensitivity. Stress strain curve look identical. So now that's natural rubber is also not very rate sensitive because it's a crystal melting and you have to go very high rate to stop crystallization.
So that's outside of the use range that probably as well.
Yeah. Yeah. So, and now the principle, I was keep coming back to ceramic matrix composite. So ceramic matrix composite, both fiber and matrix are ceramic. They're totally elastic, but a composite itself is very tough. I haven't really studied carefully about the fatigue resistance. I don't know, Thomas, you study this. Fatigue resistance of a ceramic composite. I bet you it's not too bad. It's not too bad because
mechanisms are somewhat different, right? There's friction. Right, there's friction. There's a lot of things going potentially on at the interfaces.
Right.
And so, yeah, but I think that's probably the only way really to enhance the fatigue break growth resistance to going to a layered structure in some ways. And I think with what we have seen also in additive manufactured systems where you have sort of directed grain growth out of the with the growth direction. I mean, there are in metals, for example, there are new opportunities there, right, to use microstructure and layers, right, in the broader sense, right, to help us to deflect cracks or to steer cracks and get interaction and change the length scale gain in that sense.
Agree. Yeah. So people have known this composite structure. Of course, a composite has been around, since ancient time. Even in modern time, right? Intense development in last century. So to the extent airplane is made of composite, right? So I think people should revisit all these composite strategy. Just ask a new question: what happened to fatigue?
Good, yeah, absolutely. Yeah, that's a good point here. Yeah. Anyone who wants to chime in here? Otherwise, we could. It's still open for questions here before we maybe move over to Gather Town.
So this chat has 15 questions. Have you seen these?
I have, yeah. So I've tried to summarize this a little bit. One of the questions was regarding the initial crack question. Then were several questions for cyclic rate dependency.
Yeah.
Then were questions. One question was why choose the PAA rather than another hydrogel? Is there anything that you can maybe comment on that here?
Polyacrylamide, because we're a mechanical engineering group, we don't know a lot of chemistry. They happen to be very easy to work with. You can make very long chains easily in the lab. Even in my lab, we don't have to rely on anybody.
Okay.
Yeah.
Yeah. So then one other question was, so you definitely showed that, right, that brittle plus brittle can be tough, can mean tough, and or fatigue growth resistance. And so is there, how would you summarize this sort of general design principle? Is there is it delocalization? Or
Delocalization.
Yeah.
So the way to do delocalization is, Thomas, you already summarized it. You need to have a composite structure. Let soft material to deform, to spread stress into this hard material. Hard material is a load carrying member. So for example, if you just, if your application requires you to make a truss structure, no soft material just air. Yeah, then the stress is delocalized, right? It's delocalized to the member of each truss member. So if you make your member like a bridge, very large, the stress is not concentrated. Of course, you have to worry about a joint. You take care of a joint, as long as you take care of a joint. Yeah. So the truss structure itself is a highly fatigue resistant material. People can test that, even with metal. You can make a metal truss to make it highly fatigue resistance, right? Yeah.
I think that were sort of the. Let me see if something else was posted here.
Yeah.
There was the question of temperature.
Yeah.
So the question is, one question was, can you generalize? So that was sort of the last question. So how can you generalize this in terms of maybe, is there a predictive way to say, I have K1, I have a threshold 1, a threshold 2, or toughness 1, toughness 2, and whatever else that I need. Is there a generalized, is there a sort of a model, right? In composites, elastic behavior, let's say we know rule of mixture, right? And in toughness, rule of mixture is sort of not always correct, right? Because the delocalization changes that. It's not volume fraction K1 of one material plus volume fraction K1C of the other material, right? So that rule might not necessarily always work because we're changing on how the phases interact with each other. And do you know on how to, do you have any idea on how and what direction one would need to go with that?
So you're absolutely right. In general, predicting toughness is hard, and predicting threshold is hard. But I explained how Lake Thomas model work. It has a prediction. We have tested, other people have tested over the decades. It kind of work within, order magnitude, within factor few. So certainly if you make a chain longer, your threshold become higher. The scaling is right. Now, actually ceramic composite toughness can be predicted by this simple model. It's almost like a Lake Thomas model, right? You deconcentrate stress over long distance. How much deconcentrate depend on the shear sliding stress, and you can predict that. So, I think for several simple things, you can do prediction. Now, even without quantitative prediction, as long as you have this clear idea in mind, all I need to do is deconcentrate the stress. Then you can design many things, and the testing is very fast, right? The moment you test.
Yeah, that's so I really appreciated the idea in saying, yeah, think about it in a different way. So that's great. That's a great message to everyone.
Yeah.
We had really good attendance. We had over 100 people on the meeting for a while, and if we all move over to Gather Town, maybe there is another different form of a more informal communication that we can, if you still have time for that. And you know how this sort of how this is going to work out, the Gather Town. Have you used this before?
Maybe once with my son.
Okay, that's good. Yeah, then you're in the game here, right? So if that's okay with you, we could maybe switch that over to Gather Down, and we invite everyone who was on the presentation today to join there, and then maybe have a different kind of more informal interaction in that sense, if that would work.
Okay.
As in the name of the School of Mechanical Engineering, as we end this, we all very much appreciate your time for the seminar, the discussion with the seminar, very interesting topic, and really great insights here, and also for the individual meeting with the faculty members. It was a long day for you, and so we know you're busy, but so very, very, very much appreciated.
Thank you, Thomas. Thank you.
Okay, thank you, and see you hopefully in the other app.